Okay, I guess it's time now and we will start. So, again, I welcome Dr. Matt Santamoris for this day 3 lecture, which is only his lecture today for 2 hours. We'll have it till 1 p.m. So, I leave the floor open, sir, to you. Dr. Matt Santamoris, please.
Morning, good afternoon from Sydney.
Good afternoon. It's good morning here, actually.
Yeah. Thank you so much. Today we will discuss about mitigation and especially materials for heat mitigation. I will share my slides. Can you see my slides now?
Yes, sir, we can see it, sir.
Okay, thank you so much. So, why it is important to discuss about materials? Because the climate of the city is very much determined by the thermal and the optical properties and characteristics of the materials. The materials which are used in buildings and also in urban structures. And materials determine the urban climate. Why? Because materials are characterized by an ability to absorb or reflect radiation, and mainly solar and thermal radiation, and also because they have a capacity to store and release heat back to the atmosphere. So in this case, heat or cool down the atmosphere. Materials which really are used in cities are characterized by a reflectance. And the broadband reflectance is called albedo. And the materials albedo determine the albedo of the city. And increase of the albedo has a direct impact on the energy balance of a building. Once we have large-scale changes of the albedo of the city, may have very important indirect and direct effects at the city scale. And why this? Because materials, once they have a high albedo, they reflect a lot, can, let's say, absorb much less solar radiation, reflect much more solar radiation. So they present a much lower surface temperature, and because of the lower temperature, release less sensible heat to the atmosphere and contribute less to the increase of the urban, let's say, temperature. Materials present very, let's say, selective optical and spectral characteristics in the various bands of solar radiation. Please allow me, for those that they don't have the knowledge, to present the main, let's say, bands of the solar radiation. We have the UV radiation, which is, let's say, up to 280 nanometers. Then we have the so-called visible radiation between 280 to 750. This is the part of solar radiation that the human eye can really observe, can understand. The human eye cannot understand the other bands of solar radiation. We have the near infrared, which is from 750 to 2500 nanometers, which is very important because it contains the same amount of energy as the visible part of solar radiation. We can say that 50% of the solar radiation which comes to the atmosphere is in the visible, and the other 50% is in the near infrared. Of course, it's not exact, it's almost 50%. But the impact of near infrared is extremely important. And then we have the, let's say, meso infrared, which really for our applications, except if really we have to do with the, let's say, properties and characteristics of the urban atmosphere. So we have to understand that each material has a spectral reflectance and emittance, which are the most important optical parameters. So the spectral reflectance determines how much of the incident radiation is absorbed to a specific wavelength. The spectral emittance determines the potential of the materials to emit radiation at a specific wavelength. These are two very important properties that determine the thermal balance of the materials. What it has to be understood is that the spectral reflectance and also the emittance present different values at different wavelengths. The materials are selective. They don't have the same properties in the different bands of solar radiation. And this is very important because this allows us really to define which kind of parameters we want to use and how really to use the materials. But the materials have to be considered based on their selective, let's say, optical properties and not on their broadband properties. To achieve the minimum surface temperature of the materials, it is important to achieve the maximum reflectance and emittance. Why? Because by having the maximum, let's say, reflectance, the materials absorb the minimum of solar radiation. And why emittance? Because the materials, they have the possibility to emit, dissipate the heat which is stored in their mass. Every material emits infrared radiation, not the same way, but emit infrared radiation. So we wish the materials to reflect solar radiation, at the same time be able to emit the radiation. The emittance of the different materials is not the same. For example, concrete and the other building materials present a quite high emittance. These materials can emit the radiation back to the atmosphere and so dissipate the excess heat. On the contrary, metals, for example, present a smaller, let's say, emittance, and they don't have such a high capacity to emit the solar radiation. What has to be understood also is that the emittance at a specific wavelength of a material is equal to the absorbance of this material at the same wavelength. So if we take, for example, a material and we check how much this material may emit at a specific wavelength, for example, in the atmospheric window, 7 to 18 micrometers, we have to understand that a high emittance at this specific wavelength means a high absorbance also at a specific wavelength, which means that if really the material emits a lot at this wavelength, it absorbs also a lot at the same wavelength. So this is very important. This is the so-called Kirchhoff law that has to be understood in order really to, let's say, design the proper way let's say, materials for the urban environment. In reality, the spectral reflectance of the materials in the visible wavelengths determine the color of the materials. Because the human eye can really understand only wavelengths at the visible part. And what really it gets back and characterizes the color, it is really the reflected radiation by the material. So a material which reflects a lot, almost at all wavelengths at the visible spectrum, is a material which has a light color, can be, let's say, a white color. Materials that really present a very high absorptivity, so a very low reflectance, these materials present, let's say, high absorbance, and these materials have dark color. They are black. Then, if the materials reflect at the green, these are green materials, and so on. But because this material present in the visible part a high, let's say, absorptivity or a high reflectance, it does mean that in the infrared they have similar, let's say, optical properties. For example, a black material can have very high absorptivity and has very high absorptivity in the visible part. I'm sorry, but in the infrared part, its absorptivity may be different, may not be absorbing, may be reflecting. So this selectivity of the optical properties of the materials is something which is extremely important and defines in, let's say, at large, the main axis of the material science. So as I told you, the light color materials present a high reflectance in the visible spectrum, and the dark color materials present, let's say, absorbance. And given the color, the human, let's say, beings have really classified the materials which are used in the built environment as absorbing or not absorbing. For example, we know that black asphalt, which is black, of course, present a very high, let's say, absorbance, and so it can be very warm. But it's true that the absorbance is very high in the visible part, because what we can see is the visible, let's say, part. Perhaps this material can have a high reflectance in the infrared part. And given that 50% of the solar radiation is in the infrared part, a material like the dark asphalt or the black asphalt may have, let's say, a high absorptivity in the visible, but a very high or a high reflectance in the infrared, or may have a high absorptivity in the visible and also a high absorptivity in the infrared. Can we change the properties of the materials? Yes. We are able to change the properties of the materials by using different mixtures and by playing really with some additives. So the message is clear. Don't believe your eyes as it concerns the properties of the materials. Your eyes give half of the truth, the visible part. The other visible part cannot be seen by our eyes. Dogs can understand it, but not human beings. So it is important when we work with materials, when we consider materials for cities or buildings, to consider and take into account the properties of the materials in the whole spectrum, not only, what we see. So the myth that dark materials are really very absorbing and light materials are very reflecting, it is really true in the visible part, but not is a general truth. Because we may have dark materials which are reflecting, or we may have white materials which are absorbing in different wavelengths. So this is a very clear, let's say, message to you, and please remember it. Given the, let's say, different properties, we have really different, let's say, broadband absorptivities and reflectivities. What means broadband? The global, let's say, reflectance or the global absorbance of the materials. What it characterizes the whole material. And this is the weighted, let's say, average of the reflectivity in the different wavelengths, given also the intensity of the solar radiation at the specific wavelength. But a material which has a very high broadband reflectance is a material which presents low temperature, while a material which has a very high broadband absorbance may present a much higher, let's say, surface temperature because this material really absorbs a lot of solar radiation. Given these optical characteristics of the materials, we can really understand and we can measure their performance and their, let's say, temperature by using different experimental techniques, including remote sensing techniques like satellites, airplanes, drones, in combination with infrared thermography to measure, let's say, their surface temperature. You see a picture, for example, from the center of Sydney. You see that the red color corresponds to high temperatures, the blue color corresponds to lower temperatures. These pictures are taken by using infrared thermography. What is infrared thermography? It is really a measurement and experimental technique which really can intercept the radiation sent by the materials. And given that the radiation sent by the materials is a function of the temperature, we can really disassociate the radiation from the temperature and so understand the absolute value of the temperature. So we can have a thermal image of the material. This is very important, and this is the main technique used actually really to perform experimental, let's say, campaigns in the built environment. I'd like to show you some of these, let's say, experimental campaigns we're using in my university, but these are, let's say, very common everywhere in the world. For example, for all the, let's say, experiments we're doing in the built environment here in Sydney, we're using a drone. We're using a drone with a thermal and a visual camera. The drone may fly over the surfaces and make pictures, of the surfaces. And then based on the, let's say, characteristics of the surfaces, we can have, let's say, the temperature, and we can understand the temperature of the materials. And you see, for example, some pictures that we can take, from the area. Of course, this is not so simple. It is not just what really the screen shows. We have always to correct for the proper emissivity of the materials. For example, if camera flying over a drone with a drone and you measure the temperature of, for example, metals, what perhaps you have really got is wrong because metals present a low emissivity. So in this case, you have to enter the software of the thermal camera and make really a correction of the thermal emissivity in order to get the proper, let's say, value of the temperature. These are very basic physics that we have to use. Of course, optics is very important and has to be well understood. And before, let's say, going to the different, let's say, types of materials that have been developed the last years regarding, let's say, heat mitigation, I think that you have really to go back, understand the optics of the materials, because if you don't understand them, you will live with myths and you will use really materials the wrong way. So, since, we have understood that the temperature of our cities is increasing, we have started really to develop materials which aim to decrease the temperature in the urban environment. And of course, this is not done immediately. We started, let's say, 30 years ago by studying really the different natural materials. Materials are used in settlements, traditional settlements around the world, and people understood that light color materials present really a slower temperature, while, let's say, dark materials a high temperature. So this is the reason that in, let's say, the warm parts of the world, they used to use, let's say, light colors. So for many years, scientists, they have spent a lot of time trying to understand the thermal and optical properties of natural materials. And now I think that in every country, we have a very good database with, let's say, the characteristics of the materials in case that someone likes to use natural materials. And we are using a lot of natural materials. For example, in the south of Europe, we are using a lot of white marble. White marble is a very, let's say, cool material because it presents a very high, let's say, reflectance. And this is the reason that it's preferred, from the other, let's say, materials. However, because it has a very high reflectance, it may create some problems because reflectance, especially reflectance at 80, 90%, if it is, let's say, direct to the eye, if it is, let's say, not diffuse, may, let's say, create problems of glare and contrast. This is called specular reflectance because according to the law of reflectance, the reflected radiation, it leaves the material the same angle of incidence, So in this case, at a specific, let's say, angle, you may have a lot of radiation, and this may affect your. On the contrary, other materials present diffuse, let's say, reflectivity properties. That they don't reflect just to one specific angle, but they reflect almost in all angles. So the reflected radiation, it is distributed, let's say, all over the horizon. So in this case, we don't have problems of glare or contrast, or the problems are not so important. This is the major problem with we can surface of the materials, and we can really avoid to have, let's say, specular reflectance, and we can increase the diffusivity of the materials. But, it is not always possible to change the properties of the natural materials. But natural materials present excellent, let's say, candidates for the urban environment, provided that we are aware of their, let's say, properties and the way that have to be used. The second, let's say, group of developments that started to happen around 1990 and 2000 was really materials which present very high reflectance. This research has started really mainly in Asia, in the United States, because they wanted to have materials for the space, let's say, research, which present very high reflectance. Why? Because, for example, when we send, something in the moon or in another planet, there is no atmosphere. In this case, solar radiation is very, very, let's say, high. And in this case, we may, let's say, have materials which are not so much affected by solar radiation and so have to reflect solar radiation. So at that time, they have developed white materials, paints, and many other materials, which present very high reflectance. So these materials started really to enter into the market by the 90s and a little bit later, and still are, let's say, used. For example, in, let's say, the oil-producing countries, they paint all the tanks where they store the oil with this kind of materials. Why? Because evaporation really damages the tanks, and we may lose, because of the evaporation, 7% of the oil. So we need to have the lowest possible temperature. So these very high reflectance white materials are available into the market, and they have really excellent optical properties. Attention, it's not the color that defines the high reflectivity of the materials. For example, you can take a white paint which is based, on, let's say, metallic materials, aluminum, for example, or a white paint which really can be based on other polymeric, let's say, gradients. Both they may have a similar color, and both they may have a similar reflectance, but they don't have the same temperature. Why? Because the materials do not have, let's say, the same capacity to emit the radiation. Why? Because their emissivity is different. Metal materials present a low emissivity. They keep the heat inside them, while the other materials, they, let's say, emit the radiation. So it's not only the reflectance that define really the thermal properties of the material, it is also the emittance, and the emittance is of extreme importance, and we will come back to that. So we have a variety of different white materials now in the world, but we cannot use only white materials, in our cities. We need color for aesthetic reasons and for many other purposes. So is it possible to have cool materials, reflective materials of, let's say, different color? Is it possible to have, let's say, a cool black? Yes, it is possible. And these materials, the cool color materials, have been developed around, let's say, 2000, 2010, and these are everywhere, available in the market. How this is done? By increasing the reflectance in the infrared. As I told you, we have the visible part where 50% of the radiation is here, and the other 50% is in the infrared. A black material has a very high, let's say, absorptivity in the visible. You can't change that. If you change that, you change the color. But it's not necessary to have a very high absorbance in the infrared. We may succeed to have a very high reflectance in the infrared. So the average reflectance may be, let's say, much lower than that of the conventional material. And this is the principle, that we use to develop the highly reflective, the color highly reflective materials. We'll come back to that. The fourth, let's say, generation of materials was really the development of the materials, color reflective materials, which present higher capacity. What is capacity? What is thermal capacity? Thermal capacity is a thermal property of the materials that really determines how much of the heat which enters the material may be stored by the material. Some materials, they have a very high capacity to store water, concrete, for example. Some other materials, they don't have such a high capacity. Do we need to have a high capacity, a thermal storage capacity, which is called thermal capacitance, or not? Depends on the application. But for most of the applications we have in the urban environment, we need to have materials which present very high reflectance, very high emittance, and high capacitance. But the capacitance is something really that is a property of the materials that cannot change. Yes, but we can increase the capacity of the material by adding some ingredients, which are called phase change materials, PCM, which really keep the heat which is, let's say, entering the material, stored, and then released back. So this, let's say, generation of the materials present high reflectance, high emittance, and high capacitance. Excellent. But many people said that, okay, I can have a reflective material, I can have a cool material, and I can put it on, for example, my, let's say, roof. But it is excellent for the summer period, but what about, let's say, the winter period? During the winter period, I wish really to absorb solar radiation. I don't really wish to reflect solar radiation because we have heating needs and the radiation has to be absorbed, has not to be reflected. So what I have to do? To paint the roof during the winter and then change the color during the summer. So based on this, let's say, requirement, many scientists, they started and they developed the so-called thermochromic materials. Thermochromic materials are materials which change the color or the properties as a function of the temperature. So during the summer period, these materials can be very, let's say, reflective, and during the winter period, these materials can be very absorbing. How? We will see it later. These materials have been developed, they have some problems, are not so much, let's say, penetrated into the market, but they have, let's say, been developed. Then there are some other materials, thermoelectric materials, which are developed, and the principle is that once these materials are heated, they generate electricity. Or when they generate electricity, they store heat or they release heat. There's a lot of research on this, let's say, on this type of materials, and but fortunately or unfortunately, we don't have these materials now ready, for use in the built environment. And then the real revolution comes, the revolution of the photonic materials, materials which really present a very high, let's say, reflectance, and at the same time, a very high emittance. These materials present subambient temperatures. How? We will discuss about it. And these materials have been developed the last 10 years, and these materials really allows now to have subambient temperatures in cities. These materials are really commercially available, and these materials behave like air conditioners without the use of any electricity. These materials at the beginning were really white or silver, and because of the very high reflectance, these materials could be used only at the roof, of buildings. But now, the very last years, we have developed photonic materials which present really very high thermal and optical properties, but with color, which means that we can have, let's say, very high optical performance, subambient temperatures, but at different colors. This is really a short history of what really happens actually in material science. We can also, if you like, classify materials in three major, let's say, groups. And this is what is done by many other people. For example, the natural cool materials, which includes paving stones and other rocks, lime-based materials, white pigments, which are based on titanium dioxide, a very common material for paints, etc., etc., etc. Then we have the modern cool materials. We have the infrared reflective coatings, various white paints and coatings of high, let's say, reflectance, thermochromic materials, and fluorescent materials, materials which really, because of fluorescence, present lower temperature. And then we have a third generation or a third group of materials, the so-called supercool materials, which includes photonic materials that I presented you before, photonic materials combined with fluorescent materials to give color, and also a new generation of materials that they are not really so well developed, the so-called caloric materials that we don't have the time to go through that. So I will start really presenting you one by one the different groups of the materials, and I will start with, let's say, the highly reflective white materials, the materials that are developed in the 90s and still are available and present a very high, let's say, performance and are very much used in different, let's say, implementations. We have made a comparative, let's say, testing for about 2 months of, let's say, about 19 different reflective white paints during the summer period. And we follow the daytime temperature and we follow the nighttime temperature. Most of these materials present a very high reflectance, close to 0.9. Some of them, they had 0.95, some others, they have let's say, 85. You see, for example, in the upper graph, there the distribution of the temperature during the daytime. You see, for example, that you have some white materials which present low temperature, but you have some other materials which are also white, which present 20 degrees higher surface temperature. Why two white materials may have, let's say, such a big difference? It's not the color that makes a difference. It is the emittance that makes a difference. What I mean? I mean that even if really these materials, they have the same reflectance, so they absorb the same, in reality, whatever it is absorbed, either it is stored inside the material or it is re-emitted. It is emitted to the environment. Some of the materials, some of the paints, they can immediately dissipate the heat back to the atmosphere. Some other materials, for example, the aluminum paints, do not dissipate the heat. So after, let's say, some days of operation, if you put side by side an aluminum white paint against a conventional white paint, you will see that after 5-6 days, the surface temperature will be, let's say, the difference of surface temperature will be up to 10 degrees. Why? Because the aluminum paints have a low emissivity, which means that they cannot emit the heat. And this is the reason that these materials, they have much higher temperature. The same exactly happens, for example, with, let's say, the night period. During the night period, you see, for example, that there are materials which present up to 10 degrees higher surface temperature during the daytime. Why this happen? Because of the emittance. Because these materials keep the heat absorbed during the day and do not really emit or dissipate this excess heat, and as a result, the temperature is higher. You may ask me, why so to use low emittance materials? Low emittance materials are used for military reasons. For example, if you have a military building and for sure you want really to cover the existence of this material, of this building, or you don't like to follow, what is happening in the building by the satellites. The satellites measure the, let's say, infrared radiation sent by, let's say, the surfaces, by the materials. If the material is not sending any radiation, in this case, let's say the satellites cannot determine the material, cannot determine the building. And which material do not send infrared radiation? The low emittance material. So for camouflage or military, let's say, purposes, we're using low emittance materials because we don't like to be detected by, let's say, the satellites or detected by, let's say, the other surfaces or the other monitoring equipment. At the same time, a material which has, let's say, very low emittance, for example, a metal surface, as you remember, it has at the same time a very low absorbance, because I recall that the emittance is equal to the absorbance in the same wavelength. So a material that has a very low absorbance, if it is opaque, it has a very high reflectance, because the sum of reflectance and absorbance is equal to 1. So a material that has a very high absorbance has a very low reflectance, and a material that has a very high reflectance has a very low absorbance. So a material that has very low emissivity has very low absorbance, and this means that it has very low reflectance. So during, for example, the night, you can really watch such a material, but you don't see this material. You see the material which is next to it, or the material which is, let's say, around it. Why? Because this material is not emitting radiation, but is reflecting the radiation coming from the other materials. So imagine that during the night, you are in the army and you have a thermal camera observing, around, and you can see, for example, you can watch or you can look towards, a material or something, a military, let's say, installation. But instead of watching the military installation, you can watch trees. Why? Because the military installation has a very low emittance a very low absorbance, a very high reflectance. So it reflects to your eye or to your thermal camera the radiation coming from the trees around. So instead of watching the, let's say, military installation, you watch the trees. So low emissivity materials are very much used really in military applications, but not so much really in heat mitigation studies. So the message is clear. We have white materials which are of very high performance, and we have white materials in the market which are of lower performance. For heat mitigation properties, we use only materials which present very high reflectance and very high emittance, no metal-based materials. And you can see, for example, the role of, let's say, the emittance on the surface temperature of the materials. You see, for example, that the lower the emittance, the higher the temperature. And there is an almost linear correlation between the emittance and the temperature. If you buy and you use low emittance, let's say, paint for your roof, you will not have a cool roof. You will have perhaps low absorption, but the temperature will not be so low as in the case, of other materials. And, this is very clear once we use it in urban applications. For example, now we try really to decrease as much as possible the temperature of, let's say, urban infrastructures, streets, as you can see here. So we are using materials, coatings, which present high reflectance. Not only high reflectance in the visible, but also high reflectance in the infrared. So pavements are really the best clients of this kind of coatings. And let's say, thermal performance and the thermal balance of these materials is really determined of how much of heat is absorbed and how much of heat is really reflected and how much of heat is emitted. You see the temperature difference at your left between a dark asphalt and, a white asphalt. You see that the black asphalt presents almost 40 degrees, maybe more, higher temperature than, let's say, 30 degrees, 40 degrees, than, let's say, the gray material. So this has a tremendous impact on degrees Fahrenheit, I'm sorry. This is a tremendous, really, difference that determines really the thermal balance and finally the temperature in the built environment. So in order really to decrease the temperature in the built environment in our cities, for many years, about 10 years ago, we started really to paint streets and pavements. The biggest, let's say, implementation of these cool pavements, it happens in Los Angeles, in California, but also in many other now cities around United States, and also, also in the Gulf. You see, for example, an application that happens, let's say, in United States. There is a very important program that really tries to decrease the absorptivity of the materials and of structures in the United States, and especially in the southern parts where it are really much, let's say, warmer. Actually, the application and the implementation of the reflective materials, at the urban scale, offers tremendous, really, possibilities and tremendous, really, opportunities. And the measured decrease of the temperature is of the order of magnitude of 0.4, 0.5 degrees in average. In some cases, we have much higher. However, it is very important when cool pavements are used to consider the optical annoyance. Why? Let's say, because the drivers really, if they have to look on the reflective pavements, they may have strong problems and serious problem of glare and contrast, and this may create accidents. So usually when really we are using cool pavements on streets or in pavements, we, let's say, not use materials with a total reflectance higher than zero point 0.4 or zero point 0.5. After some time, these materials will, because of the aging, will present, let's say, a reflectance no more than 0.3, zero point 0.4. So the increase of the reflectance that we really propose for the urban environment is of the order of magnitude of 0.3, 0.4. Instead of having black asphalt, which has a reflectance of 0.05, it's much better to have something which is 0.3, 0.4. Actually, in Los Angeles, and you may, let's say, you may be surprised, we have 1 million square meters of cool pavements. And let's say the program continues. So it is really a large program that works very well. I had the chance last year to be there and work with them. And believe me, it is a wonderful program that really contributes a lot. Now, in the Gulf area and in many other parts of the world, they started really using, let's say, this technology. In my opinion, the materials that they are using in Los Angeles are very reflective. The, let's say, excuse they have is that after, let's say, 3-4 months, because of the aging, the materials they are losing a lot of reflectance. So in this case, you don't have a problem, of, let's say, optical anodes. Another important problem here is really the advection of heat, because, during a windy day, the heat or the air is coming, to the street from the adjacent other streets. So what you get really as a thermal filling is not the temperature of the air above, let's say, the pavement, but it is the temperature of the air coming from the previous street. So you may have the impact, to understand the impact of the cool pavement to the next street, where the air above the pavement is transferred, because of the motion of the wind. This is called advection. And this is very important. And this is the reason that we need to have not just one street, but we need to have, let's say, an extended application of these materials to cover, let's say, most of the city. A part of the cool pavements, which are using these first generation materials, we have the so-called cool roof. Cool roofs, and you see, for example, actually in New York, a large area of buildings with cool roofs, reflect solar radiation, reject, let's say, heat, and in this case, we have much lower temperature. Of course, the performance of cool roofs depends very much on the ambient temperature and humidity, wind speed, and precipitation, and many other things. And of course, depends very much on the optical parameters and the optical properties and characteristics of the material used. We have to use materials, and I repeat it, that present very high reflectance and very high emittance. Which is the performance of cool roofs? I will show you some examples. And I will start with an experiment we done 20 years ago in Athens, when we have, let's say, developed the first time the cool roofs and the cool materials. And we installed, let's say, on the roof of a school, let's say, a cool roof. You see, for example, how it was the roof before and how it was after. You see the temperature at the same time of the roof before, that was really high, and the temperature after. You can easily understand that during, let's say, the summer period, the surface temperature of the roof before the installation of the cool roof was very close to, let's say, 50, 60 degrees. After the implementation of the cool roof, the temperature was between 30 to 35. So we had a decrease of the surface temperature of 20, 25 degrees. This is extremely important. When this is, let's say, taken into account and we measure the necessary, or if you like, the associated cooling demand and associated cooling benefits because of the installation of cool roofs, what we found is that the installation really of the cool roof in the school decreased during the summer the indoor peak temperature up to 2.8 degrees, extremely important, and also the cooling needs of the building by 40%. So cool roofs provide a very, very important benefits really regarding the, let's say, dissipation of heat to the atmosphere and also the cooling needs and the thermal comfort inside the buildings. And I'd like to show you, for example, in a comparative way, how it was the temperature before, and these are real recordings of the temperature, the red part, and how really the temperature, the surface temperature changed after the installation of the cool roof. You see that there is a tremendous temperature difference. I know that in India there is a national program of cool roofs for schools, etc., and this is very useful, and this is really an excellent way to improve comfort and decrease the cooling needs and provide, let's say, the best possible quality of life to the students. Can we use cool roofs in, let's say, temperate environments, in, let's say, cold environments? We tried this in, let's say, an industrial building in the Netherlands. The Netherlands is, let's say, a cold area. During summer, temperature may be quite high, but during winter, you may have temperatures which are below zero. So we installed, let's say, on the roof of an industrial building, a cool roof system. And you see that, let's say, the visual image of the before and after, and the temperature before and after. You see, for example, that while the temperature before it was close during summer, close to 50, 60 degrees, after we have really decreased the temperature down, let's say, to 30 degrees. This really helped very much to improve indoor comfort tremendously and decrease indoor temperature by, let's say, 2 or 3 degrees. But the most important, decrease the cooling needs of this building during the summer period by 73%. And you may ask me, yes, okay, you have, let's say, much better cooling performance, but what is happening during the winter period? Have you increased the heating needs? Yes, we have increased the heating needs by 5%. The implementation of conventional cool roofs in temperate climates may provide very important cooling benefits, but may at the same time, let's say, apply a heating penalty. But once really we compare the cooling penalty, the heating penalty, the cooling benefits are up to 10 times higher than the heating penalty. Why? Because during the winter, reflectance is not so important in these areas because we don't have sun. And the low temperatures are associated with cloudy weather. So the increased reflectance do not really affect so much the temperature of, let's say, the materials and the temperature of the building. What about if really we implement at the city scale the, let's say, cool roofs? If really we have a national or, let's say, a regional program of cool roofs, what we may expect by, let's say, implementing cool roofs at the city scale? What we have seen from, let's say, simulations, because for the time being we don't have such a, let's say, large-scale cool roof implementation all around the world, is that on average, the use of cool roofs, and these are simulations from Athens, Greece, may, let's say, decrease the summer temperature of the city up to 2 degrees. So this is very important. On average, it is between 1 to 1.5 degrees to 2 degrees, let's say, in very warm climates. But the most, probable decrease you may have with an extended implementation of cool roofs in a city will be close to 1.5 degrees. This is another study that we have performed for the Ministry let's say here in Australia, trying really to understand the cooling potential and the characteristics of, let's say, cool roofs all around Australia. So we have, let's say, simulated the the energy performance and also the climatic performance of cool roofs in 6 major Australian cities. And we have understood which is really the expected decrease of the temperature, the energy impact, and many other things, together with the help, of our friends from the University of Calcutta. What we found is that in Australian cities, and especially in Sydney, we may, let's say, decrease the peak temperature during summer by 1.5 degrees. You may tell me that 1.5 is not so high. I can tell you that is very high, because 1.5 degrees may correspond to a cooling demand of 25%. So 1.5 degrees is really very, very high and contributes a lot. But we don't have exactly the same performance everywhere. For example, in warm climate, like for example, Brisbane, the average, let's say, decrease of the temperature may be much higher than 1.5 degrees, maybe 1.7, 1.8, and in some cases up to 2.5 degrees in some areas. Cool roofs works very well in warm climates. Works also well in, let's say, less warm climates, for example, Melbourne, but helps a lot. For example, in Melbourne, which during summer do not present such a high temperature like Brisbane, for example, the expected decrease of, let's say, the ambient temperature is close, let's say, to 0.7, 0.8 degrees. But this is really very important. There is no reason really to use dark roofs in climatic conditions, because dark roofs do not really offer any benefit. Dark roofs increase the temperature of the cities and increase the cooling demand also of the cities. So we have tried really to calculate the penalty that it is imposed to buildings because of the winter penalty. And we calculated, the energy benefits for 17 different type of, let's say, buildings here in Australia, take into account the heating penalty, the cooling penalty, and finally the total, let's say, energy benefits. Of course, this depends on the type of the building. A low-rise office building without roof insulation may, let's say, benefit up to 35% of the energy needs. So in this kind of building, you may, let's say, decrease the energy consumption by 35%. You may have a small heating penalty, but you have a tremendous, let's say, cooling benefit. But for a high-rise office building, the benefits are much, much less, are very close to 3%, because really you have benefits only in the upper part of the buildings. You have some penalties because of the heating. So the benefits are close to 7%, but don't underestimate this 7%. It is really very important. It's not only the cooling load, because not all the buildings are really air conditioned. We have free-floating buildings, and in this case, and in India, most of the buildings are free-floating. It is very important to decrease indoor temperature, especially during the summer period. We have measured and calculated the maximum decrease of the indoor temperature because of the implementation of, and we have seen that it is possible in, let's say, a non-air conditioned in free-floating building to decrease the demand really for cooling, the indoor temperature up to, let's say, 10 degrees. So it is of extreme importance, and this is measured. It's not something really that, let's say, is just calculated. So it is of extreme importance to, let's say, consider that we can have much better indoor conditions and save lives because really of the benefits. If we compare really the cooling, let's say, benefits against the heating penalties, you will see, for example, that for, let's say, tropical climates, Darwin, for example, the cooling benefit is tremendous, 90 kilowatt hours per square meter per year, and the heating penalty is almost zero. For Sydney, The cooling benefit is 28 kilowatt hours, while the heating penalty is 2.5. And in Hobart, which is in Tasmania, a very, let's say, cold climate, the cooling penalty the heating penalty is higher, 5 kilowatt hours, than the heating penalty. So in these areas, perhaps we can avoid really to use, let's say, cool roofs. But it's not just that. Because of, let's say, the lower temperature in the atmosphere caused by the cool roofs, air conditioning is working under lower operational conditions, lower temperature operational conditions. And you may know that the performance of the air conditioning is a function of the temperature. So the lower the temperature in the atmosphere, the better the performance really of the, let's say, the air conditioners. So we seen and we calculated that the, let's say, large implementation of cool roofs in Australian cities may increase the performance of the air conditioning by almost 10% or a little bit higher. So 10% better performance means a lot of energy, means much lower cost. However, cool roofs are not really free of problems. Because of the aging and because of the deposition of dust, because of the deposition, of different other, let's say, parts, cool roofs are really losing their optical properties. We have a problem of weatherization or aging. You see, for example, one experiment that we have done where really we install a cool roof, and after some years, we measure the, let's say, degradation, the optical degradation of the cool roof, and we compare it with a fresh cool roof. You see, for example, that there is an important difference, and this is really something that shows that cool roofs have to be maintained and at the same time have really to be, let's say, changed, or they have to be, let's say, improve their performance from 3 to 4 or 5 years, depending on the material which are used. But an important issue that has to be also considered is that cool roofs, because of the deposition of dust and the deposition, of aerosol from the atmosphere, especially, in polluted atmospheres, we have really, they create some, let's say, problems of microbiological pollution, because microbes and other, let's say, pollutants and, let's say, fungi, etc., that exist in the atmosphere, they are deposited, on the surface of the cool roof, and they may, let's say, create some, let's say, important, let's say, areas with higher microbe, let's say, concentration. And analysis have shown that this can be, especially in school, a little bit, let's say, risky for the kids if they go there and they put their, let's say, hands. So from time to time, for example, in India, with unfortunately most of the cities we have a very high pollution, the cool roofs, they have to be cleaned with, let's say, just water, or they have to renew, the, let's say, the material used. It is very important to consider that really we may have an optical degradation. Before stopping, for the break, another important performance and benefit of the cool roof, especially when this is associated by, let's say, by cool roof, by photovoltaics, is that because of the reflectance, let's say, of radiation, and because of the lower surface temperature, they improve tremendously the performance of the photovoltaics. We've seen that the use of cool roofs in, let's say, in areas where we have photovoltaics, improve the performance of the monofascial photovoltaics up to 6%, and the, let's say, performance of the bifacial photovoltaics up to 16%. The benefits of cool roofs in India. There is a very nice study which is done by the World Bank, which really has calculated the performance and also the benefits of cool roof in India. As I told you yesterday, and I repeat it today, the wide implementation of cool roofs in India may save up to 317,000 lives and also associated with 68 million tons of CO2. At the same time, may, let's say, help to provide an average of 186 additional labor hours per household per year, which means a lot of, let's say, additional income for these, let's say, people. This is almost 23 extra working days for people, and this is also very important. This, it is translated, according to the study, to $22 billion in productivity gains between now to 2030, and almost 8 billion annually from now to 2030. So the benefits are very high, the cost is very low. Fortunately, in India, materials, excellent materials for cool roofs are industrially produced and you can use it. So it has a very high added value for the country. Before moving to the next generation of materials, I will make a small stop here for 5 minutes and you may ask me questions if you want really to ask.
Anybody has any doubts? Anything you want to ask? Sir, there is a query. Sir, is this true for high SRI white paints too? The glare
I'm
is
sorry?
Is it true for high SRI white paints? The glare issue that you mentioned about white marble, is it true for high SRI white paints?
Depends. The marble, usually, the natural white marble, it has a very high specular reflectance. Most of the paints that we're using for cool roofs are diffuse. So you don't have the same problem. If really we use specular reflectance materials, this may give us, important problems of, visual annoyance. But usually the materials we're using are diffuse, and most of the industrial materials we have now are diffuse. I have to tell you that the problem of optical allowance in a building, for example, in the city, we may use the materials that I will present you later, the second generation, which have much lower reflectance and same, let's say, cooling performance, but without really have this, let's say, optical allowance. The materials I just present you are materials which are developed in the 90s. Now we have much better materials.
Sir, I have a query. Yeah, Pooja, you can ask. You have raised your hand. You can ask. If you want, you can unmute and ask.
Thank you, ma'am. So that was my question on glare issue of white paints and which you mentioned about the marble. I also wanted to know your opinion about using these paints. How much temperature difference can be maintained, because I feel that because of rains and dust and so much of weathering, the efficiency must not be very high. That's just my opinion. I mean, I don't know science behind this, but I wanted to know from you, how do you see wide scale adoption of white paints?
If I have understood, you are asking me which is the temperature, let's say, benefits of white paints?
So I'm asking that rains or dust might affect the property of the paint. Does it affect that property? If, for example, I've applied white paints and there is regular raining, or there is dust on the terrace, then does it affect the thermal property? Because
Yeah, understood.
yeah.
The different technologies of paints. You can have very simple paints that can be affected, by rain or by pollution, and you have a really fast weatherization. And in the market now, there are paints which are self-cleaned. and present much better performance. And, the aging properties are much, much better. So it depends on the quality of the paints. In the market, there are paints which present excellent, let's say, performance. And in this case, you don't have really these weatherization problems. But depends really on the quality of the paints. All the paints are not the same. It's not the color really that defines the quality of the paints. There are many other parameters that define the quality of the paints. So the answer to your question is yes and no. You have a strong problem of weatherization once you are using, a bad quality or an old paint, but you may have excellent quality or excellent performance once you are using, materials of better quality. For example, for the oil storage tanks, we are using materials which present, a very, very low weatherization. We change, the let's say the material every 5 or 6 years. Or for space applications, you never have this problem. So it depends on the quality, on the type, of the material you are using.
Okay, sir. Thank you so much.
Sir, I have a query. When you did your research on the physical parameters like reflectance, absorbance of the coatings, did you try to compare it with the declarations made by the product company and assess whether they were true or not?
Yes. You have to know that in United States and in Europe, we have the so-called Cool Roof Council. The Cool Roof Council is a council that really measure the performance of the materials and certifies the materials. So if you, let's say, Google Cool Roof Council, you will see a very high list of materials available to the market by different companies, tested by the accredited labs with, let's say, certified performance. So once you're using this type of products, you have to be sure about really the optical and thermal characteristics. If you're using materials which are not certified by accredited labs, you may have surprises. I have measured, and I have said, because I was the one that established the Cool Roof Council in Europe, and I have measured more than, let's say, 500 different, let's say, materials for accreditation. I have to tell you that most, of the industrial materials present, very good performance and very close to what really the company is claiming. But unfortunately, there are some other materials, that they are completely different, they have completely different performances than what really it is mentioned by the company. So my advice is that that you have to use only accredited products.
Okay, sir. Right. Okay. Thank you, sir.
Other questions? If not, we'll continue.
Yes, sir. We could continue, sir.
So we move to the second generation of materials, reflective materials which present really low temperature. These are the cool color materials. You see, for example, materials of, let's say, standard, normal, and conventional, let's say, fabrication at the left, and the cool materials, the reflective materials, at the right. They have exactly the same color. Why? Because we don't really change the optical properties in the visible. If we don't change the optical properties in the visible, we don't change the color. But what really we change are really the optical properties of the material in the infrared. For example, let's take one material. Let's take, for example, a yellow material. Let's say the optical reflectance of the yellow paint in the visible is the one shown there. We don't change this, because if we change the reflectance in the visible, we change the color. But in the infrared, and I recall you that 50% of the radiation is in the infrared, the reflectance of the material, of the conventional material, is this one. We have succeeded to increase the reflectance of the materials in the infrared. So in this case, we have tremendously increased the broadband reflectance of the material. And this is for the red, this is for the black, this is for the green, this is for every color. The result. See the comparison, for example, of two black surfaces. This one is conventional, and this one is reflective. This one, it presents about 25 degrees higher temperature than the reflective one. And also watch and compare the surface temperature of a reflective against a conventional blue tile. You see that the surface temperature, the difference is about 15 degrees. So how this is achieved? By using infrared reflective pigments in the mass of the materials. And in this case, we have a tremendous temperature difference. For example, for materials of low solar reflectance, black for the materials, we may, let's say, achieve to decrease the surface temperature up to 10 degrees. These materials are commercially available. You can buy it from everywhere, are extensively used all around the world, produced also in Israel, in India, and really present very, very high, let's say, performance and very high stability. These materials can be used, let's say, for roofs, for tiles, etc. I will show you one of the first applications we had in Europe about 15 years ago, where we rehabilitated, rehabilitation of an urban park. The temperature in the urban park before, let's say, the rehabilitation, you see it was quite high during the summer, up to 35, 36 degrees. This was really the ambient temperature. To rehabilitate the material, the park, we, let's say, we developed some infrared reflective tiles. These are tiles which are used really in the park, but these tiles are infrared reflective. They have exactly the same, let's say, color like the conventional ones, but once really we compare their, let's say, temperature difference is really very, very high. For example, see the temperature of, let's say, the old pavements of the same color and the temperature of the pavements which are reflective. So you see, let's say about 7-8 degrees of lower surface temperature. As a result of the implementation of these materials, we succeeded to decrease the temperature in the coastal area by, let's say, 2 to 3 degrees. And this is a real project. This happens, you know, at the beginning, let's say, of the new century, at the end of the old one, the beginning of the first of the new century. This was the very first implementation of cool materials in Europe, and the project won the European Environmental Award. These materials, I repeat, exist in the market, are produced, and also I think that these are also commercially available in India and are also produced in India. To further enhance the performance of these materials, we, let's say, included phase change materials in the mass of these, let's say, paints or these kind of materials. And by using, let's say, PCM phase change materials, we increase the capacitance of these materials so they can keep, let's say, the heat inside their mass. These materials have been developed, and you see, for example, this is the ambient temperature tested, and this is the temperature of the conventional materials, the temperature difference of the conventional materials, and the temperature difference of, let's say, the PCM materials of the conventional materials. By using these materials, we can really further decrease the, let's say, surface temperature of the infrared reflective color materials that I presented you before, 3 degrees. Also, these materials are available into the market and are used for tiles all around the world. However, one of the major, let's say, issues we have is really the use of, let's say, dark surfaces in streets. And you see what is happening in Los Angeles, that they really coat the street. But by coating the street, you have to do it every 1 or 2 years, and you have a very important aging. Is it possible to develop, let's say, cool asphalt materials, asphaltic materials which have a lower temperature? These materials are developed, we developed these materials 15 years ago by using, let's say, infrared reflecting pigments in the mass of these materials. And these materials were really developed, and you can see, for example, the performance. You see the visual, let's say, image of these materials, and you see the, let's say, the temperature of these materials. You see that there's a tremendous difference, for example, between black asphalt, which has temperatures around 80 degrees, and a material which is asphaltic, exactly the same mechanical properties, but it has temperatures, up to 40 and 50 degrees low temperature. These materials are really developed and are used now for, let's say, pavements and streets all around the world, and present much lower surface temperature. We have a variety of these materials where the reflectance of the conventional black asphalt is 5%. Now we have materials which present up to 55%, let's say, reflectance and exactly the same mechanical properties. I'd like to show you a project that we had in Athens about 10 years ago, before moving to Australia, where we had an extended, let's say, implementation of these asphaltic materials in the center of Athens. This was a project of 35,000 square meters. It was a very big project. And we used these materials, and the result is that we have succeeded to decrease the surface temperature of, let's say, the ash of the street by about 11 to 12 degrees, and decrease the temperature in the street by 1.5 degrees. This is really of very high, let's say, performance and very high results. But this is done, let's say, 10, 15 years ago. Research continued, and many researchers, they try really to develop smart materials that may change the color as a function of temperature. And these are the thermochromic materials. Thermochromic materials may have any color you may wish when temperature is low, and became white during the summer period. So they change the color, and so they change the properties, the optical properties, and they change their surface temperature. These materials are developed, and I'd like to show you the comparative, let's say, results, let's say, against conventional materials, cool materials, the ones I show you in the second generation materials, and also the, let's say, thermochromic materials. With the thermochromic materials, we succeeded to decrease the surface temperature up to 21 degrees. A tremendous, really, performance and a tremendous, really, impact. These materials are commercially available, but they have a small problem. They have a problem of fading, of really fast weatherization. They're losing their optical properties very fast. After 3 or 4 months, they may, let's say, fade. They may lose their, let's say, color, and from, let's say, any color you may have, for example, a pink one may become white. So they are losing their properties. The last years, there is important research that we have carried out, and we found really some optical filters which are used now on the surface of thermochromic materials. And you can see that after, for example, 30 days, the loss was almost zero. So there is a very, let's say, good opportunity for these materials in the future. But although these materials really started to be, let's say, commercially available and produced mainly in China, unfortunately, the, let's say, development of the new generation of materials, the so-called photonic materials, has really, let's say, stopped almost the development of this technology. So we move to the very last technology of materials, which in reality it is a generation. Yesterday I explained you a little bit the idea of the photonic materials. The idea of the photonic material is based on, let's say, on the development of materials with very high reflectance, up to 95%, but materials that once they emit, imagine that this is a material, when a conventional material is emitting, the emitted radiation goes up to the atmosphere, but because the atmosphere is full of gases, pollutants, aerosol, etc., this radiation, it is absorbed or reflected and re-emitted back. So in reality, a very high part of the emitted radiation returns back. So in this case, you don't have so many benefits. You have benefits, you've seen the benefits before, but we don't have really, a tremendous really performance. Photonic materials, they stop emitting at the whole wavelength. This is the solar spectrum, and this is where really the materials emit. They emit here in the infrared. Once they emit here, the radiation is coming back. But there is something magic in the atmosphere of our planet. At wavelengths between 8 to 13, the radiation emitted by, let's say, materials or by the ground surface can escape to space. Why? Because let's say, the Earth is transparent to this wavelength. Do not absorb here. Do not re-emit. Do not reflect up to 80, 90%. So imagine that we have a material that is very reflective in the solar spectrum, but do not emit here like the conventional material, but can emit here. So the whole, let's say, heat which is stored in the mass of the materials, it is dissipated directly to the space. We send the excess heat to the space. This was the idea. And this means that these materials should really emit a lot in these wavelengths, in the atmospheric window. So you see, for example, the emittance and the transmittance of these materials. So in the atmospheric window, these materials, they have a very high, let's say, emissivity. These materials started 10, 12 years ago, maybe a little bit later. And they started really for different other applications, electronics, health applications, etc. The so-called metamaterials. And these were really materials of extremely, let's say, high cost, very expensive materials, very sophisticated materials, different really to be used for building applications, and different to be, let's say, developed at the same time. These materials succeeded to, let's say, emit in the atmospheric window, and as a result, they presented really subambient surface temperature. But the first generation of photonic materials was really a generation of materials not appropriate for the built environment. The last, let's say, 5, 6, 7 years, we have succeeded to develop photonic materials for the built environment. And these materials are composite materials. These are materials which first include components which help to to reflect up to 95% of the solar radiation, but also emit at the atmospheric window. So these materials that have been developed the last 5, 6, 7 years, for building application present up to 15 degrees subambient temperature. I'd like to show you some of the materials we developed here in UNSW 3 to 4 years ago with my students. And these were really composite materials. It's not so important to show you, let's say, the chemical composition and how these materials are used. But these materials had a very high solar reflectance, 97%, and a very high emissivity in the atmospheric window, 0.9%. So these materials are tested under the Australian sun in, let's say, the desert conditions and for an extensive period. And I'd like to show you, let's say, the results. During the daytime period, these materials presented, this is the ambient temperature, this is the temperature of the materials. During the daytime, these materials presented up to 8 or 9 degrees surface temperature below the ambient one. It's a natural air conditioning without really the use of any, let's say, of any air conditioning. During the night, these materials may present up to 15 to 20 degrees lower, let's say, surface temperature. Recently, we have succeeded to, let's say, develop some simple paints together with some colleagues from the UK, simple paints which really can be used everywhere, and low-cost paints which present a very high reflectance in the solar spectrum and a very high emittance in the atmospheric window. Testing of these materials, extensive testing of these materials, shown that these materials can have up to 5-6 degrees, this paint, 5-6 degrees lower surface temperature during the day, lower than the ambient one, subambient temperature, and up to 15 degrees lower temperature during, let's say, the night. I'd like to show you a video. These materials are now used in, let's say, in London by the red buses. And we use these materials, they use these materials in order really to reflect solar radiation and also decrease the temperature inside the bus and minimize the use for air conditioning. I'd like to show you this small video. Hope it works. From, let's say, many buses this summer, and now we analyze to see really the performance. The performance seems to be very promising. This is, let's say, a new paint that is going to be commercially available the next month. But is there a problem with these materials? Yes, there is a problem with these materials. Because of the very high reflectance of these materials and the very high emittance in the atmospheric window, when these materials are used in temperate climates, may, let's say, present important winter penalties, or may, let's say, impose very important winter penalties. The analysis we have performed together with our colleagues from, let's say, the University of Calcutta, shown that these materials may decrease the temperature, during the summer period up to 3, 4, 5 degrees at the city scale, but may increase may, let's say, decrease the temperature also during the winter time up to 2 degrees. And this is an important problem because really the heating penalty may be important. Is there any alternative, let's say, to such a problem? Can we solve this problem? Yes. The recent research that has been carried out has developed, new materials which do not present such a high reflectance. So by reducing the reflectance of the materials, first, we have a better, let's say, aesthetic performance, but at the same time, we don't have, the optical allowance. And also, we, let's say, decrease very much the, let's say, heating penalty, or we, let's say, completely, let's say, minimize the heating penalty. How this can be done? This can be done by substituting, by integrating in the material fluorescent, let's say, components. Why fluorescent components? Because fluorescent materials, they have a property. Once, radiation falls on the mass of these materials, immediately this radiation, it is re-emitted at different wavelengths. So the temperature of the material is not increasing, or is increasing, very, very low. So these materials do not absorb heat. They send it back. They don't like heat. These quantum dots and other fluorescent materials have been integrated in the mass of, let's say, of the photonic materials we had. And the result was, first, that we decreased the reflectivity, but also because these materials, the fluorescent materials, constitute pigments, because pigments absorb a lot, we have colored photonic materials. So by developing color photonic materials, which are composed by three layers in reality: a solar reflective layer, and also a fluorescent layer and an emitting layer. So we have this material, which is really a reflecting one in the lower part. We have the fluorescent one, which really emits fluorescent radiation, but also gives the color. And we have also another layer, which increases the, let's say, emissivity in the atmospheric window. We have developed different color materials of, let's say, fluorescent and photonic combination. I don't like to show you all the details. I'd like to show you just, let's say, the type of the materials. These are plastic materials, but can be paints, can be whatever you want. And these are the properties. You see that the emissivity in the atmospheric window is very, very high. The reflectance is close to 97%, and also present a very high fluorescent capacity, which means that they re-emit immediately, the radiation which is absorbed. These materials are really tested under the last summer under the Australian desert. And you see, for example, the let's say the measurement equipment. And I'd like to show you some of the results. For example, we tested in a comparative way the conventional, let's say, super cool white materials, photonic materials, the ones that they have subambient temperature, the color fluorescent photonic materials, and the conventional materials. You see the results. For example, an orange, a color, let's say, material present exactly the same temperature with the white photonic material, which means that we can have the same, let's say, benefits of the photonic materials at any color. And this is done for almost, let's say, all type and all colors of the materials with small differences. However, I'm sorry, what is very important, and I like to show you, is really the comparison of these, let's say, color materials against the conventional white paints, a good conventional white paints. Imagine a red color material which present 3 to 4 degrees lower surface temperature than the conventional white paints. So now in the built environment, we have the capacity from the technology point of view to use any color we wish at very low surface temperature with very high cooling performance. Same results for different type of materials. Also, other researchers, they have developed photonic materials under the form, for example, of plastics. You see, for example, a material which is developed in the University of Wisconsin, which is a plastic material which present up to 15 degrees lower surface temperature than the ambient one. Actually, we have, and this is done by an American company, some, let's say, smart shading devices, which are extensively used all around the world, composed by photonic, let's say, moving shading devices. I'd like to show you, let's say, a small video. I hope it works. I have the advertisement. I'm sorry about this. I can't stop it. Yeah. So you see this, let's say, flying shading device. This is, if I'm not wrong, in San Francisco. You can have this flying. The components are really fluorescent metallic components, which can be, let's say, extended the way you wish and can provide shading. But it's not only that these materials provide shading. The surface temperature of these materials is 15 degrees, 10 to 15 degrees below the ambient one. So they provide cooling. Once you are below this material, you receive the coolth, from these materials. So you can have shading at any place you may wish, really. And a part of the benefits of shading, you have also the benefits of cool materials. And now, if I'm not wrong, there are about 30, 40, large applications all around the world with, let's say, very interesting results. It is impressive. Yeah. There are different and various, developments of photonic materials. From paints, you see, to materials which are very sophisticated, ceramic materials, etc., that are used for different implementations. We have succeeded really to, let's say, have subambient temperatures up to, let's say, 10 degrees. 15 degrees is perhaps an exaggeration, but 10 degrees is fine. A major problem with these materials is really that the performance of these materials in very humid climates is a small problem, but still really can operate. I'd like to show you an interesting project that we have carried out here in Sydney by using, photonic shading devices, not moving one like the ones you see before. So we had really to improve comfort in a separated in a street, in the city of Sydney. So what we have done, apart of, let's say, putting, cool pavements and greening, etc., we use some photonic shading devices. We use materials which we have incorporated, photonic, components on it. So these materials, they present 15 degrees or 10 to 15 degrees surface temperature below the ambient one. So once you've been below, this shading device, a part of the benefits of shading, you receive the coolness from these materials. So we provided comfort. We have not decreased the temperature further, but we increased tremendously comfort. This is a real project that really succeeded to, decrease the temperature, improve comfort in the area by, about 30 to 35%. And this is very important. These shading photonic device materials are now commercially available. And we use these materials in a large project we have in Mecca, in Saudi Arabia, where really we try really to improve comfort conditions. We remember that last year we had about 1,200 deaths, because, of the overheating. Another important implementation of cool materials is in Riyadh. I presented you yesterday, where we used the super cool materials on the roof of the buildings, and we succeeded together with some greener techniques to decrease the peak temperature up to 4.5%, and also decrease the, the energy consumption of the building between 17 to 35%, depending on the materials. I have already discussed about it. Also, a recent study that was carried out by the, the Australian government, shown that the implementation of these materials at the city scale here in Sydney may, contribute to decrease the cooling demand of, the city between 30 to 50%. This is a tremendous, really, decrease of the demand. But the most important is that once these materials are implemented, on low-income houses, and unfortunately in Australia we have a lot of low-income houses for the First Nation people, the so-called Aboriginals, or for low-income people, living in cities. Once these materials are used, on the roof of these materials, and this is really something which is measured, we may decrease the indoor temperature up to 10 or 12 degrees. So instead of having people living at the 40 or perhaps 45 degrees, we can really decrease the indoor temperature during the peak time up to 10 degrees, save lives, provide comfort, and at the same time, improve the quality of life of these people. There is an important study performed by our colleagues from the University of Calcutta, trying really to simulate the use of these super cool materials, photonic materials in Kolkata in India. And the study have shown that really the implementation of these materials in India and under humid climate may reduce really the temperature, the peak temperature of the city between 0.5 degrees to 1.5 degrees, which is really extremely important. So where we are now regarding the development of materials, we started really with the white, high reflecting materials in the 90s. And with these materials, we have succeeded to decrease temperature of cities up to 0.5 degrees and surface temperature close really to 3, 4, 5 degrees. Then we continue with the infrared reflective color materials, the second generation I showed you, the color infrared materials. In this case, we succeeded to have, let's say, an improved performance with a decrease of the temperature up to 1 degree, and at the same time, and let's say enhanced decrease of the surface temperature. And then we developed, the infrared reflective asphaltic materials, which also improve the performance. And then the thermochromic materials provided really very, very high performance. And you see that we can really have much, much lower surface temperature and important benefits regarding the ambient temperature. There are some problems of stability with the thermochromic materials, but the thermal performance is really very good. And then we move to the photonic materials, which really help very much the daytime radiative coolers, as we call it, to decrease the ambient temperature of cities up really to 2.5, 3 degrees, and combined with other, let's say, mitigation technologies to decrease the temperature up to 4 degrees, etc. So in reality, we have tremendously improved the target from, let's say, 2.5 degrees maximum mitigation potential we had some years ago. Now we can decrease the temperature of cities up to 4.5 degrees. Another technology that I have already presented to you is the photovoltaic really technology, photovoltaic pavements, which really may help to provide electricity and substitute, black asphalt or black materials, and at the same time have lower temperatures. So in conclusion, 10 years ago, the surface temperature of cities were somewhere here, and these are really measurements. The use of infrared reflective black surfaces really helped to decrease the temperature. And then the use of PCM also decreased the temperature. The black surfaces, also the thermochromic materials, decrease the temperature a bit. By using, let's say, advanced white materials, we had better results. But then we had the revolution of, let's say, photonic materials. So in a period of about 10 years, we succeeded to decrease the average temperature of cities up to 30 degrees. So we are ready now to decrease the temperature of cities up to 30 degrees, provided really that these materials are implemented. I'd like to stop here. Thank you very much, for your attention, and I'm ready really to reply to any questions you may have.
You all can either type your message in the chat box, or you can raise your hand and unmute yourself and ask. It was very intense for me, so I really do not have any doubts or anything. I think it's something we need to adapt to our context and try to work or research on.
Digest.
Yes, digest. That's the first thing.
Yeah, hello. This is Prem Sagar. I have two questions actually. So in one of your slide, you have mentioned that this white roof helps to reduce the indoor temperature. So how it's comfort during nighttime or early morning system? And second, is there any nature-based solution you found in your research study, like people are following to reduce the indoor temperature in their houses, in the urban areas?
Yeah, about, let's say condensation during the morning, because once the temperature is very low, you have condensation. In areas with very high humidity, you have really to reduce a little bit the emissivity, because what really defines the early morning temperature is the emissivity, because you don't have solar radiation. So in this kind of, let's say, cities, you don't have to use materials with 0.9 emissivity. If you decrease it to 0.6, 0.7, you have the same performance, without these problems. The very last years, there are, let's say, some new technologies for the materials that really include in the mass of the material some, let's say, some components which really absorb, let's say, the humidity and do not allow to have condensation. This happens. Now, about pollution. Pollution is a serious problem, for the materials, for any kind of materials, everything. in pollution, which can be artificial, chemical pollution like in India, or dust deposition, for example, in Riyadh or in Kuwait. This is a serious problem. Dust deposition is something that you can clean it. Okay, you have better performance. But chemical deposition, and it is a serious problem. And I think that for the time being, we don't have data. For the time being, we don't have the experience. I'm extremely interested really to have a demonstration project somewhere in India, in a polluted city, implement these materials and see the aging, how really these materials will perform, because of the pollution, and try to identify really ways to improve the performance. But because these materials are not really implemented under these environments and are implemented in, let's say, cities which do not have such a pollution problem, we don't have enough data.
Yeah, thank you.
Welcome. Any other question?
Anyone wants to ask any questions? Well, Professor, I think we need time to digest all that you have presented.
Okay, to help your digestion, I will send you a book that we published some years ago about heat mitigation materials for free, and you can distribute it.
Right. Okay. So we will have lots of things to digest, and then the amount of work that has gone into every single sentence that you have said. Forget every single slide. So
Yeah,
we
this
will.
is very very specific. I understand this, but it is very important to, let's say, demonstrate the progress we have. It's important to know that there is progress, not to live with myths. And, this is very important. And those that they are interested, they can go really and further study. There is industrial research in India on it. There are some very good companies really that they are accredited by serious, let's say, institutions, and they produce very good paints, really. So there is progress. I think that cool roofs and cool pavements for India is a wonderful technique because it's cheap. It's very cheap. You can go to informal settlements and you can use these materials everywhere. For example, in United States, in Pennsylvania, for example, for low-income houses, they give them the paints for free. We discuss now with the government of New South Wales really to install all this in houses, the Aboriginal people. So it's a wonderful technique. I know that in India there are many applications. 2 years ago, we had the big conference, on cool roofs in India. So there is a lot of progress. I think that you have to intensify the research on it. If you don't really, you don't have the resources, or it's not so easy really to implement the very sophisticated materials. It's not a big problem. Gradually can be done. India is an industrial country, goes to the moon, can produce paint so easily, it's not a problem. But because of the cost, and especially for informal settlements and low, let's say, income people, perhaps we can use a previous technology, but this is one of the cheapest and the best technologies we may have, for mitigation.
Right. Right. So I'm not getting any doubts, but then people are really appreciating the intensity and the amount of information that we have got today. So if there are no doubts, then may I take this opportunity to thank Dr. Matt Santamoris for sharing so much of knowledge and wisdom today, and then also showing that as academicians, we are not here only to give lectures, but actually be on site, conduct research, and share the data that we have got out of the research. Thank you so much, sir. Thank you.
Yeah. Tomorrow we start 2 hours earlier, isn't it?
Yes, sir. You start a little early. Shall I tell you the exact time, sir?
No, 1:30, Australian time, is it?
Okay. I'll tell you, Indian time is 9 o'clock, so it should be 1:30. I will just.
Okay. I will be in another city tomorrow. I will be in Melbourne, but no problem. Yeah.
Yeah, so tomorrow is, yes, sir, 1:30 Australian time, sir.
Yeah. Okay.
Okay, thank you so much. It's on green and blue technologies for heat mitigation.
Yeah. This is also a very interesting, very interesting group of information, package of information, because there are so many myths around it. And yeah, I think that tomorrow we will have a very interesting discussion.
Right. Thank you so much, sir.
Thank
Thank
you.
you. Thank you.
Bye, everyone.
Bye, sir. Bye. So, dear participants, tomorrow we start at 9 a.m. Indian Standard Time, and sir is the first one to speak tomorrow. Okay? Right. Thank you all. Thank you. I will leave. Take leave.